Today we have a lab expose, whatever. This is about the tools that you use in the lab. You have to be familiar with the tools that you use, or you're not going to be able to understand the concepts that we're trying to show you. And the first one is this little DMM. The digital multimeter. In other words, this is a device for measuring electrical components. And these meters right here are very sensitive in the sense that they're pretty accurate. At the same time, they're real cheap. This one is about $75 compared to some of the other meters you can get. Now, I guess I moved it to my office. I did have one in here that the initial price on it's like $4,000. But anyway, as I was saying, the meter is your basic tool for all electrical components and qualities except the watts. I still have not found a digital meter that will measure watts. Those require their own special meters. But if you'll notice, on the face of the meter, there are several settings. There's odd because there's 2 settings for voltage and there's a whole like 6 settings for current. What's going on? Well, what's going on here is that anything with the sine wave above it is for AC. Anytime you see a symbol with that sine wave above it like that, it is specifically for AC. Now, on the DC side, this meter has both the solid bar and the broken bar, the dashed line. Those tell you 2 different things. The one thing it tells you, the solid line, tells you that it measures just regular old DC current and DC voltage like you'd get out of a battery. The dashed line, however, tells you that it will accurately measure a pulsating DC circuit. Now, one of the things about DC, you know, we talk about DC all the time, it's either there or it's not there. A pulsating DC circuit does that in a specific pattern. All our internal electronics, phones, TVs, computers, everything, they all run on a pulsating DC circuit, not on a continuous flow of power. Yes, there is a continuous supply of voltage and current that's coming out of the power supply of the device, but the individual components are not always using that whole thing. And when they communicate with each other, they communicate in a pulsating DC signal. Now, that pulsation causes some meters to have fits. It will not accurately measure them, which is worse than not measuring them at all. But this one will accurately measure that pulsating DC, and that is why it has the pulsation bar across the top of the symbol. Now, this meter obviously also measures ohms. There is a capital Omega on there to tell you measure ohms here. But before you can measure anything, you have to get the leads attached to it. One of the things about all DMMs and all analog voltmeters is that the black lead goes in the common and it stays there. It does not ever move. Black lead goes in the common. The red lead moves. It depends on what you're measuring as to where you put the red lead. If you're measuring volts or ohms or any of the other things this meter reads, it goes in the jack with the red insert in it on the left. If you are measuring current, it goes in the jack with the yellow insert in it, and this meter will beep at you to tell you the red lead's in the wrong jack. So if you're trying to measure current, and you got it over here, meter beeps at you. If you're trying to measure voltage, and you got it over here, the meter will beep at you. So you need to be aware of which jack you have this red lead plugged into at all times. Now you notice that I have two different kinds of leads attached to this thing. That's not because I like using two different kinds of leads. I actually hate these pistol grip things. But since we have them in the lab, I may have to explain to you how they work. You put your thumb on the base, and you hold the shoulders of the thing, and you squeeze, and you look at the end, and you'll see a little copper hook come out of there. And that little copper hook is what you attach to whatever it is you're trying to measure. So, today what you're going to measure is ohms. That's the only thing you're going to measure, ohms, today. So, that's what we need to talk about. Let me get my giant display resistor out. This is my giant display resistor. Big enough to see from the nosebleed seats. You may not be able to read it from back there, but at least you can see it. And at one point in my career, I never thought I was going to have to explain this to anybody. But then I had somebody who didn't understand. Whatever you are attempting to measure must be between the two leads. So if you want to measure this resistor, the resistance of it, you must put one lead on one side of the resistor and the other lead on the other side, like that. Whatever you are attempting to measure must be between the two leads. Now, I read this color code, and this color code is yellow, violet, red, gold. Yellow, violet, red, gold. That is a 4.7 kilo ohm resistor, plus or minus 5%. So when I turn my meter to ohms, and I look down, it's got big numbers on it. And the big numbers say 4.85. 4.85. 4.85 what? You cannot merely look at these numbers and make a determination. Down here, in the lower right-hand corner of the screen, it will tell you 4.85 what? It'll answer that question. In this particular instance, it says kiloohms. Okay? So 4.85 kiloohms is how much this thing is. So it's within tolerance. It's a good resistor. It can be used. If we needed a 2-watt resistor in some. So today you actually are going to learn how to do two things. You're going to learn how to measure ohms, and you're going to learn how to use the basic function of the Protoboard. That's what we're doing today, which is why you're getting kind of a lecture in lab, so that because the stuff's in front of you, this isn't something that I feel comfortable presenting strictly on the net. So you will get it live, as it were. Alrighty, so Protoboard. What is a Protoboard? Protoboard is a plastic place full of holes that we use to build circuits. We use these things so we don't have to solder. We use these things so we don't have to have an octopus riot of alligator clip leads on our desks. These things make life a whole lot easier. But using these things is not intuitive. These things are kind of strange when you look at it. You look at it first, you say, there's a whole lot of holes on that thing. How am I supposed to know where to put what? Okay, that's what we're going to talk about now. How do I know where to put what? Oops, I went the wrong way. And you are correct, sir. While I'm here, I should probably do something about that. Okay, this is where I want it to be. Now, what we're about to do today is look at this Protoboard and take some measurements to see what we get and how we get it. First of all, you will notice, or you will see, that the Protoboard is composed of a bunch of little holes. There's 5 holes. Then there's a divider of some kind. And that divider actually has a purpose. The divider actually has a purpose. When you are in digital class next semester, that's the only part of the Protoboard you can use when you're in digital class. Everything has to straddle that divide. So that's why it's there. And then down here, we have 5 more holes. That are lined up. Each one of the holes on this side of this Protoboard, each one of those 5 holes is connected to the other 4 in that group. Each one of these 5 holes down here is connected to the other 4 in that group. And they are not connected to anything else. They are not connected to anything else. They aren't connected to the holes that are right next to them. Even though you look at it, you go, well, they ought to be connected. They're right next to each other. Nope. Nope, there's no connection between this bunch and this bunch. When you're out here in the field of the Protoboard, the only connections are right there. So how do we use this thing to build circuits? Well, the first thing is you got to have a circuit to build. And probably the simplest multi-component circuit out there is a 2 resistor series circuit. So I picked 2 resistors here, and using these 2 resistors, I'm going to show you not only specifically how the Protoboard works, but I'm going to give you a couple of tips on building a circuit too. And the first one of those is that this should be a gap of about 10. That should be a gap of about 10 spaces. And if you look, they're numbered. If you look closely, they are numbered. Now, these eyes can't see these numbers anymore even with these glasses, but they are there. So, we come out here. We got another bunch of 5 out here. I'll connect them this way. And again, even though it's not drawn to scale, obviously, that should be a gap of about 10 spaces. So, we take our first resistor, and we're going to put it right there. We're going to put one leg in each hole. And then because it's a series circuit, we're going to make sure that they're connected at exactly one end to each other. So we're going to take the second resistor and we're going to put it right there, just like that. So now we have our two resistors in our circuit. So I want to measure that. I want to see what my total resistance is. Don't need this anymore, so it can go away. I take my meter, and it doesn't really matter with the meter which end you start with, because resistors are not polarized devices. So we don't worry about polarity. All we worry about is the fact that this is an ohm meter. And I take my leads, one here and one here. Now I connect them probably to the legs of the resistor. There's no sense using jumper wires today. So I connect them to the legs of the resistors, and now I read my meter. And this is where things get tricky. Because all your lives, you have been taught that 1 plus 2 equals 3. That's what you've been taught your whole life. 1 plus 2 is equal to 3. Well, most of the time it is. But when you're looking at an ohm meter or a voltmeter or an amp meter, 1 plus 2 is not necessarily 3. 1 plus 2 is somewhere between 2 and 4. You only get exact measurements that match your calculations by accident. And I can tell you right now, if you go through and you do calculations on a lab later on, and your measurements are too close to your calculations, you're going to measure that whole circuit again with me watching you. I've been teaching a long time, and 99.9% of the time when somebody gets answers that are within 1/100th of a unit of what they calculated, they're pencil whipping the lab. They're cheating. So if something like that starts showing up on your lab, probably the wise thing to do would be, Mr. B, come over here. Mr. Love, I need help. That would be the wise option. So, this meter then will show something between 2 and 4. Probably, if these two were each 10%, it's going to be somewhere between 2.8 and 3.2, somewhere in that vicinity. Maybe a little bit more on either side, depending on your individual meter. Because don't forget, just like there is tolerance in that meter, or in that resistor, and we tell you what the tolerance is, or the company tells you what the tolerance is with the 4th band, just like there is a tolerance in each one of those resistors, there's also tolerance in your meter. So you always have to take that into account. And that's what I mean. Most of the time I say 2 plus 2 is 4. In the math lab over here, 2 plus 2 is somewhere between 3 and 5. That's why I say that. Okay, so that is what would happen if we were looking at a series circuit. We would see an increase in the resistance. So what if I don't want a series circuit? What if what I want is a parallel circuit? We're going to talk about that. If I take this resistor out and move it, come on, colors, come on. If I take my resistor and move it over here, now what is my meter going to say? What's my meter going to say now? Just like this drawing is up here, what is my meter going to say?
I'm just guessing. Electricity takes the path of least resistance. It's going to go through the 1 kilo ohm.
Almost. However, what did I tell you when I said with this resistor? How does your meter have to be connected? It has to be connected across what you're trying to measure, right?
Right.
It has to be connected to each end of what you're trying to measure, right?
Right.
We didn't move the meter.
You have an incomplete circuit.
It's an incomplete circuit. This meter is going to read. Yeah, this is specific to the meter that you have, this OL. Some people are going to tell you that that means overload. Some people are going to tell you that that means open lead. Either way, what it means is this. Infinite. It does not now and never has meant zero. Folks, zero is a legitimate measurement. If you don't see a zero, don't put a zero down. OL means that the resistance is so great that it cannot be measured. That is what that OL means. And if you leave this thing hanging, that's what you're going to get. So, what we have to do is move the black lead. To here. And when I move that black lead to there, what you were talking about with the path of least resistance, now it's going to read somewhere around 670 ohms. Going to read somewhere around 670 ohms. With these two resistors. And that's because of the way parallelism works. Parallelism, what happens is that the weaker resistor starts carrying as much current as it will carry. And the next resistor up starts carrying current until it can't carry anymore. And then if there's a third resistor, it starts carrying current till it can't carry it anymore. And all this happens down in nanoseconds. So it's kind of like being on a highway. But that's what you got. And that's how it's going to react. So what I'm telling you is when you take this very first two circuits you're going to build in here, this little series circuit and this little parallel circuit, when you measure the first one, your resistance should be close to the sum of these two. When you measure the parallel circuit, it's actually going to be lower. Don't let that surprise you. Don't let that shock you. Okay? So, now we're going to talk about the red and blue bars. Some of these red and blue bars, these Protoboards are so old that they are fading away. They have been rubbed off. For instance, the one I have in my hand here probably has, instead of the 4 that are supposed to be there, it probably has 14. Because through the years they've been rubbed into dashes and not a solid line from one end of the Protoboard to the other. If you find a Protoboard that has solid red and blue lines from one end to the other, that means that that board is continuous. That bus, those are called buses, that bus is continuous from one end of that Protoboard to the other. That's what it means. However, there are Protoboards out there and I'm just going to put 3 of them on each side over here. Where that line is not continuous. And that means that bus bar is not continuous. Instead of the bus having 4 buses like this one does, a Protoboard that is marked like this has 8 short buses. And my suggestion of what to do with the short buses, if you have a Protoboard that has short buses, my suggestion is jumper wires. Make those short buses long unless you have a reason to have 8 short ones instead of 2 long ones. Because what will happen is you'll get invested in building the circuit. Okay? And you get concentrated on the circuit. And so you get the circuit built. Now this isn't necessarily true in here, but next semester you'll see what I'm talking about. You'll get invested in building that circuit, and then you'll turn it on, and half of it works. You're like, why the hell did the other half of this thing work? And the very first thing you're going to do is tear that circuit down, because in your mind you built it wrong. I don't care if you had every wire in the exact place that it needed to be, you will tear at least part of that circuit down because you're going, I had to have done something wrong. But you never think about the Protoboard. You never think about the Protoboard. So that's why I say, if you get a big Protoboard that has split bus bars, get 2 little bitty jumpers and close that gap. Get rid of it. Now, the reason I have a resistor drawn up there, like I do here, is to show you what happens if you put a resistor in your power bus. If you put this resistor in the power bus, and I want you to do it when we get around to it. If you put this resistor in a power bus like this, that really is 0 ohms. 0 ohms. Why? Because you shorted that resistor out. You've got both ends of that resistor in the same set of connected holes. It's going to short out. You can do the same thing with the 5 vertical holes. You put both ends of resistor in those 5 vertical holes, you're going to short that resistor out. May as well not even put it on the Protoboard because it ain't doing a damn thing. So, this is the end of Unit 1. Oh no, complete circuit first. There is a whole lot of BS out there about what constitutes a complete circuit. Pure and simple. I don't know if these people are ignorant or if they're liars. But either way, they're wrong. I have actually read textbooks. This is one of the things when I review a textbook, the first thing I do is go and look at their definition of a complete circuit. And if it has more than these three things in it, I do not go any further because there's no sense in it. The author is an idiot. You will hear that a complete circuit requires a source, some kind of conductor, a load, an insulator for the conductor, some kind of overcurrent protection, and then a control. No, no, and no. A complete circuit does not require any of those three things. All it requires is a power line laying on the ground, a water puddle, and a thirsty dog. That's all it requires. And you're going to take a collie and turn him into a poodle. Don't listen to anybody who tells you got to have that conductor's not insulated. Okay, the circuit is not safe. But safe and complete aren't the same thing. They are not the same thing. Keep that in mind. This is the end of Unit 1. Now what we're going to do, Mr. Love and I are still to some extent working on this. Here's how we're going to do this. The test will be posted over Unit 1. The Unit 1 test will be posted the Monday following. So Monday, actually probably Friday because we're off Monday, assuming you can prod me enough to get me to write this thing. The test will be posted for you to do. You'll have that whole week. I do not put time limits on tests either. But everybody who thinks I'm being generous is deluded. You have a whole week to do the test. Do not come to me the Monday after unless you have in your hands proof that you or somebody in your immediate family was in the hospital and you were there the whole time. Do not bring me anything else and say, please let me take this test, because the answer is no.